Okay, so in today's class, we're going to talk about solubility, what solubility is in terms of concentrate. Yes, sir. Yes, sir. In terms of concentration of solubility and how to interpret solubility curves or data that's presented to you. So in the first thing that we're going to talk about is solubility is really defined as the amount of solute that is able to be dissolved in a particular amount of solvent at a certain temperature. So how soluble something is depends on the temperature and its ability to actually be dissolved. So if we say something is occurring, like if we take a glass of water and we set it out on the table and it's at room temperature, the question is, how much solute can you put in there before it won't dissolve any further? So, and that's kind of what solubility is. So imagine, if you will, you take like sugar and you put it, you take your glass of water, right? And then you take sugar and you start adding tablespoon after tablespoon after tablespoon of sugar in there. So you add 1 tablespoon of sugar, you wait for it to dissolve, and it dissolves. Then you add another one, you wait for it to dissolve, and then it dissolves. You add another one, you wait for it to dissolve, and then maybe it dissolves a little bit, but it doesn't quite completely dissolve. You can tell because there's still some in the bottom, but it's not completely all there. Then you take another one, and eventually it doesn't dissolve anymore. So no matter how much you put in there, it will not continue to dissolve. And that's what solubility is. And there is a limit to how soluble a substance can be based on a couple of factors. One of them is the amount of solvent that is present really dictates the amount of solute that you can put inside of it. Okay, so if more solute can be dissolved in the same amount of solvent, then the solubility would say to be increased. So in my example here, I would say like sugar, if more sugar can be dissolved in the same amount of solvent, water, solubility is increased. So if less solute, less sugar, can be dissolved in the same amount of solvent, then the solubility is considered decreased. Okay, so that's kind of what we're talking about here. Now, there are 3 major factors that affect solubility or how well something can dissolve in water or in another substance. And the first one of those is temperature. So remember, temperature is really a measure of the amount of energy that a system has. So if we increase the temperature of the system, what happens to solubility? Well, the easy answer is solubility increases. So if we add more temperature, or we increase the heat, or we add more energy, solubility of a substance will increase. So why? Well, we are adding more energy to the solvent. And by adding more energy to the solvent particles are moving faster. So if the solvent particles are moving faster, that means that more fresh solvent is going to come into contact with the solute. So think about it like this. If I take my water and I take sugar and I increase the temperature of my water, the water molecules are going to be moving faster. And so when they move faster, they're going to collide with the container walls, but they're also going to collide with the solvent, the sugar, more. And by doing that, it creates an opportunity for those intermolecular forces of attraction to be overcome, which means it will dissolve. So adding more energy to the solvent makes the solvent particles move faster, and brings fresh solvent to the solute. And since the intermolecular forces of attraction are polar or the same, or non-polar or the same, right, then we can overcome the intermolecular forces of attraction more. So So the intermolecular forces of attraction of the solute are more likely to be overcome, and then the solute dissolves at a faster rate. So if we want something to dissolve slower, we can do the opposite, which is cool the substance down or the system down. So that's one of the ways that we can affect solubility. We can increase and or decrease the temperature. All right. Another way that we can increase or influence solubility is if something is stirred or agitated. Okay, so stirred, agitated, shaken, etc. Okay. So what happens when a system is stirred? Well, what happens when a system is stirred? The particles that are of the solvent are forced to move, and when they're forced to move, fresh solvent comes in contact with the solute. So that means that if we stir something or agitate something, we will increase the solubility. Now, the why part is kind of important, is that the stirring or agitation forces the new solvent particles to come into contact with the solvent. So the stirring, and by doing that, by forcing new solvent particles to come into contact with the solute, the intermolecular forces of attraction are overcome. And the solute dissolves. Now, that doesn't necessarily mean that it won't dissolve on its own. It just means that we can make it dissolve a little bit faster, or we can make more of it dissolve. And then the last factor that can affect solubility is crystalline size and or surface area. Okay. So if we increase the size of a crystal, or at least the surface area of a crystal, what happens to solubility? Well, if the surface area is increased, solubility will also increase. And so what do I mean by that? I mean, if we take a substance Like, you know, the brown sugar, when you take the brown sugar out of the bag in the baking section at the house there, and it comes out in one giant hard brick. You know what I'm talking about? You ever seen that before? Brown sugar, hard brick. Think it's useless. It's kind of not. It's just been wet. So what ends up happening is if you take it and you crush it, and you crush it into smaller chunks, you increase the surface area. And if you increase the surface area of the brown sugar, more solvent particles can come into contact with it instead of in one specific area. Another example would be like a sugar. Well, actually, a better example would be something like aspirin, right? You're not supposed to chew aspirin, but you all know that one uncle that does. You know what I'm talking about? Maybe that uncle's your dad. No, it's still gross. But like the reason why you're not supposed to chew it is because when you ingest aspirin or Tylenol or whatever, it's in a pill form because they want it to release over time. So when it says that you get like 4 to 6 hours of pain relief from aspirin, you're getting 4 to 6 hours of pain relief over time because it's taking that amount of time for it to dissolve. Okay. But if you crush it up by chewing it, which you're not supposed to do, it will dissolve faster and have less of an effect over time because it'll get absorbed faster. Does that make sense? Ish. So increasing surface area increases solubility because there is more access points for the solvent to come into contact with the solute. And if there's more access points, that means that the solvent and the solute will interact more. And if they interact more, the substance will dissolve faster. So tried chewing an aspirin once and I thought it was disgusting. So I don't recommend it. It doesn't taste good. It's kind of burny. All right, so those are factors that can affect solubility. So it's surface area, temperature, and agitation. Okay, those are the three things that affect solubility. You should be aware of that. Now we're going to go on to a couple of examples and how we use our newfound information, which is solubility curves. So here is a handy dandy solubility curve that almost every chemistry class gets an opportunity to see because somebody made this like a million years ago, and it's so good that we just keep using it. We don't like make a new one because why would you break something that's not broken? You know what I'm talking about? So anyway, in this instance, you are asked to determine how many grams of sodium nitrate will dissolve in 300 grams of water. Now, there's a couple of things that we have to keep track of here. First of all, this 100 grams of water is technically the amount of solute, or I'm sorry, solvent, is the amount of solvent present. So if you can imagine that, like in this scenario, we have a bucket of water, right, that's has a mass of 100 grams. And so all of the data on this graph is in this one bucket of, is in a bucket of water the same volume or the same size. Does that make sense? And so then what happens after that is we can determine how much stuff can be dissolved in that scenario at those temperatures. So what I'm going to do is I'm going to read what I have and try to figure out how to get there. So the question is, how many grams of sodium nitrate will dissolve in 300 grams of water at 40 degrees Celsius? So what we have to do is we have to, first of all, figure out what we're looking at here. There's so many things on here, so I'm just going to focus on this line right here for this problem. Oop, that's terrible tracing. That's better, okay? Because I'm focusing on sodium nitrate. The other thing that I'm focusing on is the temperature in this particular reaction. So I see that I'm going to take 40 degrees and go straight up, and then I'm going to go straight over, and I'm going to say that it looks like in 100 grams of water, about 95 grams, nope, I lied, 105 grams of sodium nitrate will dissolve at 40 degrees Celsius. So that's what this tells me. So the graph tells me that at 40 degrees Celsius, about 105 grams of NaNO3 will dissolve in 100 grams of water. Okay. So how are we going to figure out what will happen in terms of 300 grams of water? And some of you can look at that and just have already figured it out, but some of you are like, well, there's got to be some math involved because it wouldn't be chemistry class if it wasn't mathy. So I'm going to make a ratio and a proportion, really. So 100 grams of water can hold about 105 grams of NaNO3. So on the other side, if I want to figure out how much sodium nitrate can be dissolved in 300 grams of water, I would say question mark grams of NaNO3. And you guys are all like, oh, I know what I can do there. I can do some sweet cross multiplying, right? So I'm going to take the 105 times 300, and I'm going to get something like 31,500 grams, and that's going to be equal to, looks like 100 grams times question mark grams of NaNO3. So clearly we're going to divide both sides by 100. And it looks like we can dissolve 315 grams of NaNO3 in 300 grams of water at 40 degrees Celsius. That's not going to be true for another temperature, but that's true for that temperature. Does that make sense? All right, we got another problem, another sample, another situation. So here we're looking at a different line, and this says at the time it says how many grams of water will be needed to dissolve 150 grams of potassium nitrate at 50 degrees Celsius. So again, I'm going to highlight the line that I need to focus on, and so I'm looking for potassium nitrate, which happens to be this line right here. And then what I'm going to do is I'm going to draw a line up and over to try to figure out what I know at 50 degrees Celsius. So I'm going to take like 50 and over, and I'm going to say at 50 degrees Celsius, I can dissolve about 85 grams of KNO3 in 100 grams water. But the problem is asking me something about 150 grams of KNO3, so I'm trying to figure out how much water. So in this case, I'm going to write my proportion as 85 grams of KNO3 in 100 grams of water, And I know that I have 150 grams of KNO3, and I'm trying to figure out the amount of water I need. So 100 times 150 is 15,000. And we're going to divide again. And we are going to get this time a value somewhere in the ballpark of 176. Let's see, 0.47, but sig figs because there's 2 sig figs in the problem. So it's really going to be like 180 grams of water is what we're going to need. All right. There's a third one that's a you try situation. It's a you try. So you give it the old college try, the old GHS try. So, in this situation, I got 127.5 grams of potassium chloride could be dissolved in 100 grams of water, which is true, but with sig figs, it ended up being 130 grams of potassium chloride and 100 and 250 grams of water. Sig figs matter, I suppose. All right, last slide here is simply just looking at data and then trying to decide what's more soluble versus least soluble. So in this first example, we're looking at the solubility curve between HCl and KNO3. So here's KNO3. Looks something like this. Here's HCl. And the question says, at 30 degrees Celsius, which one is more soluble? So I'm going to go 30, just go straight up like this here. And it looks like HCl, because it crosses its line of solubility, crosses the 30-degree threshold higher up, that means it's going to be more soluble. So in this case, the correct answer would be HCl is more soluble. In the next example, we're looking at NH4Cl and KCl. So NH4Cl and KCl, NH4Cl, and we're looking at 70 degrees Celsius. So I'm going to draw a line at 70 and just kind of make an assessment. And it looks like NH4Cl is more soluble than KCl because it's higher on the graph. And then lastly, looking at the solubility curve, what is the least soluble substance on here? And so I don't even need to like look at one specific thing at 10 degrees Celsius. I'm just going to draw my line up like this, and I'm going to see the lowest curve that crosses it, which in this case happens to be KClO3. So KClO3 is the least soluble substance. On this graph. So that's that. So your homework tonight is to do the next worksheet in the packet. It is a one-sider. It's got some math problems. It's got some reading a graph like this problems. It shouldn't take you very long. And then the other thing that you have for homework tonight is to complete the lab and make sure you're ready to turn that thing in tomorrow.